Okay, so imagine that we have two linear operators, capital lambda and capital omega. Those are our operators. And we're going to take those two operators and we're going to operate on a vector state. So I can write down lambda and omega, and they're operating on our vector state v. So we have to be very careful with operators, the order in which you operate with them matters. So in this case, I'm first going to operate with the omega, and then the second step is to go in and then operate with lambda. So like I said, that order matters because it could be, depending on what the operators are. I haven't specified what physically omega or lambda really mean, but depending on what they are, this could be totally different from if we first operate with lambda on V and then operate with omega afterwards. So for example, if I operate with omega on V and I get a new state which I could call W, and then I operate lambda on W, I could get a totally new state called Z. However, if instead I operate with lambda on V, then I could get a state which, I don't know, we could call W prime. And then if I operate with omega on W prime, I could get a different state like Z prime. So an example of that, a more concrete physical example of that, could be our rotations. So if we have our Cartesian coordinates, x, y, and z, and then we want to take a rotation around the x-axis by 90 degrees. So we could have this rotation r by 90 degrees around the x-axis. We could also have a rotation of 90 degrees around the y-axis. So we could take z and rotate it 90 degrees around the y-axis. Now we're rotating around this different axis. So if we did a combination of those two, we could get a totally different result depending on the order in which we apply those rotations. So let's say we apply a rotation around the x-axis on the x-axis. So remember, x we're going to call state 1, y we're going to call state 2, z we're going to call state 3. So first I'm going to rotate. Okay, so we're going to rotate first around the x-axis with a 90-degree rotation around the x-axis, and then second we are going to rotate with a 90-degree rotation around the y-axis. So I'm showing here pi over 2 with the j hat. So I'm showing a rotation around the y-axis. So first, the rotation of around the x-axis applied to the x-axis is just the identity. That doesn't change the x-axis. So now I have my rotation of 90 degrees around the y-axis acting on the x-axis, and then so a 90-degree rotation around y in the x direction gives me basically the z direction. So I'm rotating this x-axis into the z-axis. So now when I try and reverse that, why don't I apply a 90-degree rotation around the y-axis on the x-axis, the state for the x-axis, and then after that I will apply a rotation of 90 degrees around the x-axis. So when I do that, the first step here, so this rotation around the y-axis applied to the x-axis gives me the z-axis. So now what I have is a rotation around the x-axis applied to the z-axis. So when I do that, I'm now rotating the z-axis into the y-axis. So you can see, so the whole point of this example is that the order in which we do these rotations matter. If we first rotate around the x-axis and then follow that up with a rotation around the y-axis, our answer is we are now pointing in the z direction. But if I rotate about the y-axis first, then after that I rotate around the x-axis over here, then my result is that now I'm pointing in the y direction. So the order of operation matters. Usually the test for that, the test to see whether or not the order matters, is something called the commutator. So the commutator is drawn as these square brackets where I take these two operators, omega and lambda, and I basically compare operating with lambda first and then omega second to if I operate with omega first and then lambda second. So it's basically your commutation relation that you've seen since the 4th grade, but now applied to operators. So if you were to operate on a state, so I have some vector state v, and I'm operating with the commutator, then what I would have is something that looks like this, where now I'm operating on basically both directions. I'm operating first with omega on v, followed by lambda on the result of that, and comparing it to lambda first operating on v, and then the product of that I'm operating with the operator omega. If this is equal to 0, then obviously the order doesn't matter. It doesn't matter which direction, which order, whether omega operates first or lambda operates first. So before I end this section, what I wanted to go over is what if we have 3 linear operators? So these three linear operators I'm going to call theta, lambda, and omega. So now when we do, why don't we try and see what happens when we apply the commutator of omega on the product of lambda and theta. So basically what that looks like is, well, I take omega and then lambda theta minus, now I take the second term, lambda theta, and operate with omega. So that's kind of the way that the commutator is written. So the first term is the left operator followed by the right operator minus the right operator followed by the left operator. So we can try and reduce this a little bit more if we notice that I could write this first term here, omega lambda theta, as the commutator of omega and lambda plus lambda omega, all that multiplied by theta. So if you think about it, let me go back and do this again. The commutator for omega lambda is omega lambda minus lambda omega. So I can just isolate the omega lambda up here if I add to both sides lambda omega. So omega lambda is equal to the commutator of omega lambda. Sorry, let me clean that up. The commutator of omega and lambda plus the product of lambda omega. So I'm going to take that and put that in up here. And that's how I got this first term right here. Okay, so let me go back again. Let's go back. So the commutator of omega lambda theta is omega lambda theta minus lambda theta omega. And so I said I'm going to substitute in for the omega lambda from above up here. And so I get the commutator omega lambda plus lambda omega times theta. And I'm going to do the same thing with the second term now. With the second term, I'm going to write this as minus lambda times, I want to replace theta and omega with another commutator relation. And that one is omega theta minus omega commutator with theta right here. Okay, and so now I'll group terms, and I'll get omega, the commutator of omega and lambda, plus lambda omega theta minus lambda omega theta, minus times a minus is plus, plus lambda times the commutator omega theta. So the second and third terms cancel each other, and what we're left with is the commutator, sorry, let me go back. There's supposed to be a theta right here. So I missed the theta. I didn't multiply that theta through. So it's supposed to be the commutator omega lambda times theta. So the commutator omega lambda times theta plus lambda commutator omega comma theta. Okay, so in the end, if I write out the result, the commutator of omega and the product of lambda and theta is equal to the commutator of omega and lambda by itself, now multiplied by the operator of theta, plus the operator lambda times the commutator of omega and theta. So if you think what we're kind of done now is something like the chain rule. We've moved those operators in and out. So this is a very important result that we're going to come back to later on in the course. Similarly, if I had the product of operators on the left-hand side, so say I want to have the commutator of the product of lambda and omega, and then commute with theta, what I would get in this case would be the operator operator lambda on the outside times the commutator omega and theta plus the commutator lambda theta, that commutator times the operator omega. And so you can kind of see that if the product is on the second term, the right-hand side, then the operators you factor out are on the inside right here. And if the product is on the left-hand side, then the operators, this time lambda and omega, are on the outside of those commutators.